This is an example of kinematics applied to uniform circular motion. Here's the problem that we're going to be looking at in this example. I have a 1.5 meter long piece of string with a sticky jawbreaker candy stuck to the end. I know that if the string accelerates the candy more than 12 meters per second, the candy will come unstuck. What's the maximum speed at which I can spin the candy in a horizontal circle over my head using the string without the candy coming unstuck? So we'll take a moment to make sure we understand the question by rephrasing it. This mentions a circle. All right, so I'm thinking circular motion. There's also a question about acceleration, and these funny units, meters per second, that's meters per second squared. Acceleration, circular motion, I'm thinking centripetal acceleration. So what the question is really asking is, what speed for an object moving in a circle with a radius of 1.5 meters produces an acceleration of 12 meters per second squared? If I can find the speed that you get with an acceleration of 12 meters per second squared, then I'll know that I need to keep just under that speed to keep the candy from breaking loose. So our next step is to organize our thinking with a picture and to coordinate the variables. So let's take a look at that next. Alright, here's what I'm picturing from this problem. Here's the person. I guess that's me. And there's the string with the candy on the end, and it's going to be moving in a horizontal circle over the head. Alright, so maybe not the world's most beautiful picture. I could draw a top view. Here's my top view. There's my radius, so r equals 1.5 meters. And I know that the maximum acceleration I can take, that's AC, centripetal acceleration, is 12 meters per second squared. And I am trying to solve for the speed. The equation that relates these things, the radius, the acceleration, and the speed, the equation you should always think of when circular motion comes up, not only in kinematics but in forces too, is that centripetal acceleration equals the speed squared divided by the radius. So I know the centripetal acceleration limit, that's 12 meters per second squared. I know the radius. I'm going to go ahead and solve for the velocity. So here's the equation that we're using. Centripetal acceleration equals the speed squared divided by the radius. So let's put our numbers in. The maximum acceleration we can take is 12 meters per second squared. That's going to equal the speed, which I don't know yet, divided by 1.5 meters. My first step is to multiply both sides by the 1.5 meters. And that's going to cancel out on this side and leave me with 18 meters squared per second squared equals velocity squared. These units look funny, but remember this is equal to velocity squared, and so we take the square root of 18, and then that's going to be meters per second, and that works out to about 4.2 meters per second for the velocity. So I gotta say, that looks kind of low to me. That actually looks like kind of a low speed. And one way to think about it is, what does that mean in the number of turns per second? Well, one full turn is the circumference of the circle, which to calculate the circumference, that's 2 times pi times the radius, which is 1.5 meters. And I worked that out, and that's about 9.4 meters. So all the way around is 9.4 meters, and we cannot go any faster than 4.2 meters per second. In fact, we actually need to keep just a little bit below that. So that means we would need to make like half a turn each second, less than that, less than half a turn per second. If we went any faster than that, the candy would break loose. This problem seems like there's no way you could spin this Jawbreaker in a circle without it breaking off the string, because this speed is just too slow. If you pictured picking up a string and trying to swing just half a turn per second, it's not going to stay up there. It's not going to work very well at all. So it's interesting to discover, I guess, that this Jawbreaker, there's no way you're going to be able to swing around in a circle and expect it to stay on the string. I think we're done with this problem.